In part 2 of the lab, we're going to look at how you can convert an image's representation in pixels into meaningful real-world data, like its length in millimeters or centimeters. Doing this isn't quite as simple as just declaring that a pixel has a certain length value in the image. You can see this effect because in this image, where I have a perfectly straight grid that I've printed out and put under the camera, there's a significant fisheyeing effect, which means that each of these lines, while they are the same length in reality, once they're captured by the image plane in the camera, are significantly distorted. And now, this length over here is going to appear shorter to the camera than this length here. Fortunately, COGNEX has included with their software a package that helps us do nonlinear calibration to get past that effect. Coming into the spreadsheet here, we can see that I've already set up two areas. In one of them, I'm going to do a millimeter-based calibration, and in the other, I'm going to do a centimeter-based calibration. To get started with this, it's easiest to just search in the palette for calib and get the calibrate grid function inserted. This is going to pull up in a dialog box, which is where we configure the settings for our grid. From here, you can generate a grid and print it yourself. I'm going to be providing one for you in class that has a grid spacing of 20 millimeters. And so as long as all these settings are set, including the width fiducial, which is in reference to this set of elongated rectangles here, so that the image can be oriented in a particular way, you are ready to do calibration. This process is really simple. All you need to do is click through to the Pose tab here, and make sure that your grid is laid out in a way that the camera is able to accurately perceive it. You'll know that it's working if it can recognize each of the kitty corner parts of the checkerboard with these little green X's, which means it's identified that those points exist and should be calibrated around. To get a new image in there, if you need to do an adjustment, you simply press the trigger button. You'll notice that it changed very slightly. And if you need to, you can adjust the region. In my case, this actually looks good. We can see that it has a nice range all the way up into the extreme corners. It isn't marking these because it's not part of the checkerboard pattern, but it is using them to perform calibration. So now I can simply push the calibrate button and I can check out the results. It gives you a report on the calibration, but it's probably best to check yourself. The easiest way to do that is to, one, finish with the calibration, hit OK, and you'll see that a calibration has been inserted. The next step is to use that calibration on a copy of the image. This is done by inserting a calibrate image function, in which case you will select the original image and then use the calibration on it by selecting that structure. Once that's inserted, you'll notice that now you have two different images. And now you need to be careful which one you're using. One way for us to verify that our calibration worked is to use the fact that each of these squares we know has been printed to basically exactly 20 millimeters in dimension. To identify that in the image, we can use the find segment function. If we select a region that contains exactly one segment, which is a point at which the contrast has changed and then it's changing again after some distance, so going from a white to black transition to a black to white transition means that there is a black segment in this region. We can see that by basing it on A0, what we're going to get is a length in pixels. So this segment is 134.6-ish pixels long. However, if I just copy this, and then I tell this edges structure to instead reference a different image, namely our calibrated image, we can now update that to give us a dimension in millimeters. So this segment is 134.6 pixels long, but it is also 20.166 millimeters long. And you can do this repeatedly. So if I were to verify a different region, namely out here where the fisheyeing effect is more pronounced, I can see that I still get a measurement of roughly 20 millimeters, which means that the nonlinear calibration has worked pretty well. Now, of course, you could keep repeating this process with different types of calibration. So in this case, I've based it on millimeters, but if I come back here into the calibration structure, all that I should need to change is in my setup go from 20 millimeters to 2 centimeters. Do the pose, trigger the image, hit calibrate, get a good score, hit OK. And now you can see that I'm still getting a pixel measurement of 134.6 pixels, but instead I'm getting 2 centimeters as my edge length in both positions. If you ever want to figure out what image a particular function is referring to, all you need to do is select it, and then this Show Dependency Levels Increase button will show you, by pointing from where it is getting its information to the function, which image it's relying on. So this edges function is relying on the image at A0. This one is relying on our centimeter calibrated image. And this one is, of course, relying on the millimeter calibrated image. This is all you should need to do for this part of the lab.